So I am going to do this problem. This is actually a problem from the textbook that I originally was going to assign to you to do, but now I'm going to use it as our notes. So this is on page 543 of the textbook. So if you want to see the original problem, it is on page 543 of the textbook, and this is problem number 1. So I'm going to talk you through it, and then you get to do problems 2 and number 3. So what we have here is we have a projectile that is moving not only vertically, but also horizontally. So up until now, we've mostly been just looking at objects that have been shot straight up and coming straight down. And so that's your typical parabola motion that we've looked at, where you throw something up in the air and then it comes straight down. Well, now we're going to be sending it somewhere. So it's going to have an X component and a Y component. It's going to have a horizontal component and it's going to have a vertical component. So here's our situation. We have an object. Here's my object. It's projected with initial velocity of 5 and 2 meters per second. So 5 meters per second in the horizontal direction and 2 meters per second in the vertical direction. So we could figure out its actual velocity and direction. We could do that, but that's not what the problem is asking us for. It's going to ask us for a couple of other things. Okay, so but we could figure out what is its actual velocity. We just know it's broken out into its component parts. We could use our SOHCAHTOA to find this angle, and we could, of course, use the Pythagorean theorem to find its magnitude, but that's not what we're going to do. Okay, another piece of information we have is that it's projected from a point 1.5 meters above the ground. So the distance here, so it's like maybe somebody is holding a rocket launcher or something, and then they're firing the rocket launcher from 1.5 meters above the ground. Okay, and these are meters per second, so everything's in meters. Okay, we can say here's the ground. And no, it is not to scale. Notice my 1.5 is bigger than my 2. So pardon the mess. Okay, so another thing that, I need to write on here that's given to us in the problem is the acceleration of gravity. So gravity is going to be affecting this projectile. So it's actually on the planet Earth, not above the planet Earth. It's actually within the gravitational pull of the Earth. It's not somewhere else out in space. So the pull of gravity, the force of gravity, the acceleration of gravity, which I'm sure you're probably all aware of, acceleration of gravity is negative 9.81 meters per second squared. So the first question asks, write the acceleration vector. Okay, so if this has an initial speed, that's just a constant speed. It's not being given an acceleration. It's just being shot, bam, it gives it initial speed. So the only acceleration that's happening is going to be that force of gravity. That's the only acceleration happening, because we are going to ignore friction. There's no friction on the Earth anymore. Okay, we're going to ignore that, make things simple. So we want to write the acceleration vector. So what is the vector for acceleration? Well, if here's my ground, right? Here's my ground. Acceleration just goes straight down. It just goes straight down. So if I think about writing a vector for gravity, so here's my gravity vector. Well, it's only going down. There's no horizontal component. So the acceleration, it's going to have 0 in the direction horizontal. All of the action is happening straight down. So that would be negative 9.81. There's my acceleration vector right there. Okay, very simple, because gravity is just going in one direction. It's just going down. So we don't need to break it up into component parts. It's just going straight down, negative 9.81 meters per second squared. All right, now we want to find an expression for the velocity. So we want to find an expression for the velocity. We know the velocity is 5 and 2, but we also know, though, that we have the acceleration. And so that means that the velocity is going to be changing. So if we know the acceleration, then how do we get velocity? Well, let's see. Acceleration is the derivative of velocity. So to go backwards, we're going to have to integrate. So we're going to go ahead and integrate to find the velocity function as a vector, okay? Both the horizontal and the vertical components. So part I, I'm going to do that part first, and then we're going to do the displacement, because after we have the velocity, then we're going to be able to get the displacement vector by integrating velocity. Okay, so we have our acceleration, 0 and negative 9.81, and I want to integrate both of those. Okay, so the acceleration, 0, I'm going to integrate 0, and we're doing this in respect to time, 0 dt. And then for the vertical component, I'm going to be integrating negative 9.81 dt. Okay, so when I integrate 0, I still just get 0 again. Okay, because even if I put a t next to it, well, 0 times t is still going to be 0. So this is going to be 0 when I integrate this. I'm going to get 0, but plus the constant of integration. Okay, now these are going to have two different constants of integration, so I'm going to call this c sub 1. All right, and then this one over here, when I integrate this, I get negative 9.81 t, because if I take the derivative of negative 9.81 t, I get negative 9.81. So, and then don't forget our constant of integration. All right, so we could say now that our velocity vector, oops, I have a slightly different setup here tonight. So let's move this. Can you see it? There it is. So my velocity vector is going to be 0 plus c sub 1, which is just c sub 1, and negative 9.81 t plus c sub 2. Okay, now we do have some information about the velocity. We know the initial velocity. The initial velocity was given to us up here. Our initial velocity is 5 and 2. This is when time is 0. The initial speed that's put on this, it's given just a bang, like out of a cannon or something. That initial velocity is when time is 0. So when t is equal to 0, we know that the velocity is equal to 5 and 2. We know that's its initial velocity. So now we can solve for our constants of integration. So for the first one, well, there is no t in here. So this one is just going to be equal to 5. Because t is 0. Well, there's nowhere to put the 0. So I'm just left with c is equal to 5. Because I need to set this one, change the t to 0, and set it equal to 5. It's going to make more sense when I do the second one, I think. Okay, so for the first one, we're going to get c sub 1 is equal to 5. And then for the second one, we're going to have negative 9.81 times t, time is 0, plus the constant of integration, or the second constant of integration has to equal 2. So notice, let's get rid of the scratch paper down here. So negative 9.81 times 0 is just 0, so we're left with the second constant of integration is just 2. So now we can write our velocity vector. Our velocity vector, the horizontal component is just going to be 5, and the horizontal component is going to be negative 9.81 t plus that constant of integration, which was 2. So there is my velocity vector. Okay, so we were able to substitute in those values or solve for those values by changing t to 0, and then we could solve for our constants of integration. Okay, so the first one's kind of weird because there's nowhere to put the t, right? So c1 has to equal 5. The constant of integration has to equal 5. Okay. The second one, when we change t to 0, means that the second constant of integration has to equal 2, because that initial velocity at time 0 has to equal 2. So negative 9.81 times 0 plus some constant equals 2, so that constant is 2. So there it is. Now we have our velocity vector. All right, now we're going to find the displacement vector. So we're going to find displacement. We're going to integrate again. So for I, we're going to find displacement. So to find displacement, we integrate velocity. And again, we're going to do it in two separate chunks. We're going to do it for the horizontal component, and we're going to do it for the vertical component. So I'm going to integrate 5, and I'm going to integrate 5 dt, because it's in respect to time, And I'm going to integrate negative 9.81 t plus 2. And that would all be dt. Okay, so I suppose I could put some displacement. For displacement, we often use the letter r. So r, and this is going to be the horizontal, and r, this is going to be the vertical. Actually, let's go back and put that on the other one, sorry. So back here where I set up those first integrals, let's go ahead and neaten this up. This would be the horizontal component of the velocity, and this one would be the vertical component of the velocity. Let's go ahead and label some of this stuff. Okay, so v sub h and v sub v. It's kind of weird. Okay, let's go ahead and label those things. And now let's go ahead and do these. We're going to integrate. So the displacement, the horizontal displacement, is going to be equal to 5t plus a new constant of integration. So I don't know, c sub 3, so we don't confuse it with all the rest of them. And then we're going to do this one, the displacement in the vertical direction. Yeah, well, I have a t here, so it's going to be a t squared, so negative 9.81 t squared. But then I need to multiply by the reciprocal of my new exponent, so divided by 2. Plus, now I got to integrate the 2, well, that just becomes 2t. And then plus, again, another constant of integration. I'll call that c sub 4. Okay, so now displacement, we know its starting position. We know where it started. At time 0, we know that it started at 1.5 meters above the ground. So we could put on here, we could put on an XY coordinate grid. So let's go ahead and do that. Oops, can you see what I'm doing? Yes, there it is. So I can put on my XY coordinate grid. That helps you to see where is it starting. It's starting horizontally, it's starting at 0, but vertically it's starting at 1.5. Okay, so this is my starting position right here. Okay, so here's the starting position. Starts here. Okay, and the initial velocity is the 5 and the 2. Okay, so back over here. So when time 0, where is it? Where is it? Its position at time 0. So when t is equal to 0, the position is 0 horizontally, but 1.5 vertically. Now we can use this, just like we did before with our velocity vector. We can use this to finish up our position vector. So we know that horizontally, it's got to equal 0. So I can say 5t plus c sub 3 has to equal 0. And then for the vertical component, I know that negative 9.81 over 2 t squared plus 2t plus c sub 4 has to equal 1.5. So this is when t equals 0, right? Oh, I should have replaced my t's with 0. So let's go ahead and do that. So I'm going to replace all those t's with zeros and then solve for the constant of integration. Because when at time 0, we know, at time 0, we know where the projectile is. We know it has a horizontal position of 0, and it has a vertical position of 1.5 meters. So negative 9.81 over 2 times 0 squared plus 2 times 0 plus another constant of integration. Okay, so if I solve this, well, 5 times 0 is just 0. So my constant of integration here is also 0. And here, that's 0, that's 0. So my constant of integration is equal to 1.5. So now we can write our position vector. So our position vector r is equal to, so my horizontal was 5t plus the constant of integration, which we just found was 0. So I don't have to write plus 0. And then for the vertical component, it's negative 9.81 over 2 t squared plus 2t plus this constant of integration, which we just found was 1.5. So there is my, oh, I just realized this thing has been in the way the whole time. Sorry, I hope this hasn't been blocking everything. There you go. Ooh, that was embarrassing. Okay, so there. Now you can see everything that I just wrote. Okay, so that is my position. This is my position vector. So this is my position vector. All right, so now there's one more part to the question. So the last part is find the time at which the particle strikes the ground and the horizontal distance it has traveled during its flight. Okay, so let me write that down. So the last part C to this question, find the time at which the particle strikes the ground and the horizontal distance it has traveled. Okay, so here we go. We can now say, well, I want to know when it hits the ground. So that would be the vertical component. I want to know when it hits the ground. At what time does it hit the ground? So that means that I want the vertical component to equal 0. So the vertical component is going to have to equal 0. So the vertical component, which is equal to negative 9.81 over 2, t squared plus 2t plus 1.5, that has to equal 0 because that's the ground is at 0. Well, this looks like kind of a pain to factor or use the quadratic formula. So I could maybe try and factor it, but that looks pretty awful. So I would use the quadratic formula, or better yet, put it into your handy dandy calculator. So guess what? I already put it in. There it is. So I typed it into my calculator, and now I'm going to graph it. There it is. And I can see, let me go ahead and zoom in. You can see that its starting point is at 1.5, because you can see that there's my tick mark for 1, my tick mark to 2. So I can see that it's actually starting at 1.5, and then it's going up and it's coming back down. So I want to find out how much time, my x is my time, how much time until it's at this point, until y is 0. So let's go ahead and calculate that. I'm just going to find the 0 of the function. So where is my cursor? I'm all logged in. Oops, going the wrong way. Should be showing up. There it is. Okay, so left bound, right bound, and guess. And I know you can't see it, but I can see it. It says that the x is equal to 0.793. So when t is equal to approximately 0.793 seconds, that's when our object will be on the ground. Notice I don't worry about the other x-intercept because that would be going backwards in time. I don't want any negative time because I started at a height of 1.5, so it's just going to go up and it's going to come back down. Okay, so that was for my vertical component. Now I want to find out, well, how far did it actually travel? To find out how far it actually traveled, now I'm going to use my horizontal component. So my horizontal component was just 5 times t. So the horizontal component is 5 times t. And so now I'm going to substitute in this amount of time that it was airborne. I'm going to plop that in, substitute that in right here. And I'm going to have 5 times 0.793. And that will get me the total distance that it traveled horizontally. So it's displacement, it's horizontal displacement. So I'm going to go ahead and put that in, 5 times 0.793. And, oh, I already had it in there. So we get 3.97 is my horizontal displacement. Okay, this is how, so my horizontal displacement here. That is how far it has traveled horizontally by the time it hits the ground. So it was airborne for 0.793 seconds. And during that time, it was moving horizontally as well, and it ended up 3.97 meters away from where it started. Okay, so didn't go very far. All right, that's it. So this is the idea that you're doing for the other two problems. You're going to do problem 2 and problem 3. And so remember, you want to separate those horizontal and vertical components, separate them. And then if you know displacement, you can take the derivative to get velocity and then take the derivative of velocity to get acceleration. But if you have to go backwards, then you have to integrate and use the information that they give you. Sometimes, you kind of got to poke around and look at that information like, oh, where's the starting point? And write that as a vector and make sure that you are substituting that in to find your constants of integration. Okay, that's it. Good luck.